So maybe we'll just get started with Ben from Stanford. He actually has been working on the crossover in the quantum optics and condensed matter, a lot of interesting physics, dynamic systems, dissipative, etc. Right? Quantum memory. Go ahead, Ben.
Okay, thank you. Let me share my screen. As you can see, I'm in California right now. There's actually a little wildfire somewhere over there, a heat wave coming by, and most people are not yet awake. I will do my best to be awake, though. All right.
Oh, just 1 second. We're gonna do the same procedure. If anyone has a question, just send me through the questions through the chat, so I can unmute you. You can just ask a question directly to the speaker at the Q&A session. Yeah, Ben, go ahead.
Okay, great. Well, thank you for attending my talk. I am giving part one of a two-part talk on associative memory with confocal cavity QED. I will be giving an overview and an update on the experimental progress. The second part will be given by Jonathan Keeling, who's a professor at St. Andrews, who will be focusing more on the theory. We have a collaboration on this topic. These are the graduate students who have been leading the effort lately: Brendan Marsh, Ronan Crozy, and Yudan Guo. And also some of the theorists that we've been closely working with are Sarang Gopal Krishnan, Surya Ganguly, and Andrew Daly, who's also in the audience right now. Okay, so let's begin. Let's see, I click, there we go. All right. So what we're talking about here is designing a neural network as a physical manifestation of a spin glass model. And it's been well known for many, many decades that the mathematics of spin glasses allow one to perform neural network-like behavior. So the idea of our work, and of course this is not original, is that if one can realize a spin glass physically, then one has created a machine that naturally realizes neural network behavior. Okay, so what is a neural network? So this is an example of one with some recurrent feedback and onto some spins. And while this looks kind of circuity, one can represent this in more statistical mechanics language with some energy functional on some spins I and j with some connectivity matrix Jij. So if this is to encode memories, then the memory patterns are encoded in this Jij matrix and manifested as spin configurations. And you can construct memories, for instance, by tailoring the structure of this Jij matrix to set a memory as an energy minimum. And then the dynamics under the Hamiltonian evolution of this class functional can guide the system to those memories and to low energy states in general. So this is the spin glass version of the circuit model of a neural network, where blue and red are, say, ferromagnetic and anti-ferromagnetic couplings. And it's known that in general, if you can make any sort of network like this, some graph of connectivity like this, then you can embed into that quadratic binary optimization problems. These are NP-complete problems. They're of interest, not just in an abstract sense, like Max Kant, but also in a very practical sense, like in protein folding or wireless communication. And there's just a very long list of these sorts of traveling salesman-like problems that one can embed in these sorts of situations. The name of the game becomes, as we discussed on this panel on Monday, to create a better wind tunnel, meaning a better physical device that provides heuristic solving capability. Not exact necessarily, but good enough compared to your competitors to arrive at solutions to these problems. Okay, so what are we proposing? So for the last, 11 years or so, we have been proposing and working on strongly coupled quantum optical implementations of neural networks using what we call confocal cavity QED. So I'll be introducing this notion to you today. This is a sketch of what that means. Cavity QED is a strong interaction between light and matter, enhanced by confining modes of the electromagnetic field between two optical reflectors. Here are these two curved mirrors. In our particular situation, we're using very specially designed mirrors such that we can support many different optical modes at the same time, at the same frequency, okay? This is called a multimode cavity, and it's confocal because that's a particular type of multimode cavity. Moreover, with these green beams here, we use optical tweezers to trap little atoms or clumps of atoms, usually Bose condensed, just because that makes it easy to manipulate, into little spots here. And those spots realize some network connectivity of the JIJ matrix that we care about. So here it's just 4 nodes here, and the photons bounce back and forth and connect them. The photons are introduced through this red pump beam here that coherently scatters light off of these atoms into the mirrors and then back onto other atoms. And then to image what's going on, we peel a little bit of the light off and interfere with some of the light emitted from the cavity to make a hologram, okay? A hologram on a CCD camera. And by reading out the phase of the image spots associated with each one of these spins, we can tell whether those spins have evolved to be spin up or spin down in real time. This, we claim, is something akin to an active quantum gas microscope. We have a high numerical aperture lens, in this case it's a mirror, that allows us to image particles or atoms very with high resolution, just like, say, Marcus Greiner does in his quantum gas microscope, but it's active in the sense that those photons get recycled back onto the atoms, back and forth, to mediate interactions between them, and I'll be talking about how that works. So because it's incredibly strongly coupled, we can create high fidelity quantum states. It is driven and is dissipative, so that might lead to efficient error dissipation or error correction in the system in a natural sense. And we drive it through a quantum or non-equilibrium critical phase transition. It's like a lasing transition, actually. It's a super radiant transition. And there's some notions that the organization at the critical transition helps you to obtain states, optimal state selection. So, okay, so this is a real thing. This experiment has long been supported by the ARO under Paul Baker and Sarah Gamble's program. This is what it looks like here. There's vacuum chambers and lasers, and this is only a small fraction of the room in which it's embedded. But this is the heart of the machine. It's a very special, one-of-a-kind type of optical cavity, very high finesse, where the top mirror can move up and down by hundreds of microns in order to put it exactly in the right spot in order to have mode degeneracy in the confocal configuration. I'll explain what that means later. There's no other machine in the world that can do this. Plus, insert between the two Bose-Einstein condensate of 10 to the 5. Now we actually get 10 to the 6 atoms, which can be diced up with optical tweezers to yield 1,000 or eventually 10,000 nodes of a graph, okay? We can even go up to 10 to the 7 spins if we want to have something that's not quite Bose condensed, okay? All right, so what are we talking about here mathematically? The basic processes in cavity QED that we rely upon are illustrated as follows. You have an atom or a collection of atoms who have internal energy levels. Let's just call it a 2-level system, a ground state and an excited state. Those couple with some position dependence to the electromagnetic field, with some interaction Hamiltonian, where there's some coherent exchange of excitation between the atomic states and the bosonic ladder of states inside the cavity with this coupling strength. And then there's some dissipation. There's a wholly bad dissipation rate, which is gamma, which is the atomic spontaneous emission rate that goes into 4 pi. And then you have a mixed bag kind of dissipation rate, which is kappa, where cavity photons can leak out. It's mixed because, of course, it does so in a well-defined way where you can collect that on a photodetector and learn something about the system in the first place. So it actually provides real-time detection. Okay, so to avoid that, that unredeemably bad decoherence rate of spontaneous emission, we usually detune very far from the excited states. So the pump field, the classical coherent pump field at Rabi coupling omega is far detuned from the excited state and undergoes a Raman and induces a Raman transition with the cavity field to another ground state. And if you make this detuning large enough, compensate with large enough Rabi rate, then basically you can have a nice strong interaction at the same time as you suppress spontaneous emission. So that's what we typically do. So the Hamiltonian, the single mode cavity QED Hamiltonian for this, it has three terms. It has the energy associated with the photon field. And this is detuned a little bit by delta, or sometimes we call it delta C or delta M, where the pump field is typically red detuned of the cavity mode. This is so that you have a stable system where the energy going in is less than the energy going out. And so the energy going out, so that energy deficit has to be made up somehow, and that gets made up either in the motion of the atoms or in the spin states, and that keeps it stable and also gives you cooling, as we'll show later. The second is the energy of in the rotating frame, the energy of the atomic state. So this is the Zeeman splitting between the spin down state and the spin up state. And the level diagram is a little bit more complicated than I alluded to. It actually is a double Raman scheme where you have two classical pump fields coupled to the G naughts of the cavity fields like so, and that yields this nice Hamiltonian. Then there's the interaction term here, which it gives you the coherent exchange between the spins of the atoms and the photons. Now, we write capital S here because we don't necessarily just talk about a single atom in the cavity. We can actually have many atoms in a particular spot and look at the collective state. I'll come back to that in a moment. This Hamiltonian is known to have a Z2 or Ising symmetry. That feeds into this notion of this Dickey model. This is an instance of a Dickey model that supports a Z2 symmetry breaking superradiant transition. So at a critical ratio of these coupling parameters, you undergo a second order phase transition where you break a symmetry. This has been seen for 10 years now, where on the photon sector, you get a burst of light coming out of the cavity, superradiance, showing that you have a macroscopic coherent population of the photon field. Concomitantly, that breaks rotational symmetry. You see that if you heterodyne that light, sometimes it's zero phase, sometimes it's pi phase. That's a Z2 symmetry. Concomitantly, you get an organization of the spin state or the motional state into a checkerboard or staggered kind of pattern, or density wave actually. So you basically get a polariton composed of macroscopic photon population and condensation into a density wave of the matter portion. Okay, so so we're moving beyond that. For the last 12 years, we've been exploring the theory of multimode cavity QED. We've developed some of the first theory of this actually. And it's a generalization of that Hamiltonian where you have many modes. So you take a sum over all the modes, and you maybe have many spins, and then you have to deal with the term, an interaction term, that's a sum over all the particles and all the modes, and it gives you some interesting many body physics in the sense that in the single mode Hamiltonian, everything is always mean field. It can be described to any accuracy you need just with kind of Gaussian fluctuations. However, in the multimode cavity, we've shown theoretically in the past that in certain situations, you get beyond mean field physics. In fact, it can even change the order of the phase transition to something called a Brzozowski transition. So interesting things happen in this multimode cavity QED sense from a many-body perspective. So in these cavity modes, these are the two-level system, and this is the atom-photon coupling. And then now, because there's some notion of space and locality, we have to consider the fact that each of these modes has some mode profile. These are the TEM modes of a cavity. And those modes of the cavity can couple to little clumps of atoms in different ways in different locations. And that's what we'll exploit to give network-like behavior. And then, of course, this Hamiltonian gets employed in this master equation dynamics to account for the dissipation. And this dissipation will be crucial for allowing the system to dynamically evolve to like the optimum of a cost functional. In this case, this physical system will be an energy functional. This is what gives you the cooling in the system. Okay, so let's talk a little bit about the cavity. So if you arrange mirrors just so, by just so I mean that the length between the separation between the mirrors is equal to the radius of curvature, you get families of degenerate modes that look like these bow ties, and you have this mirror symmetry. So all of these TEM modes that you know from Hermite Gaussian solutions to harmonic oscillators are degenerate. Well, actually only just the ones of good parity in the confocal cavity. So either the even modes or the odd modes, it's a detail, are simultaneously degenerate. And then you can take a sum over all of this, and you can get some mode spectrum here that's highly peaked. So this is not one single mode here. This is not just the Gaussian TM mode. This is thousands of modes in a very narrow bandwidth. Okay, so depending on where you set your pump, if you set it very close to this, you can resolve these modes and see that it's not quite multimode and degenerate. But if you detune far enough away, you see this looks sort of like a delta function, and then it becomes approximately a multimode cavity. All right, so let's talk a little bit about this two-level system. This is the cartoon for it. If you treat the ground states as pseudospins of just momentum, so like where the atoms are all condensed at 0 momentum or at plus or minus 1 recoil in X and Y, then you can get the manifestation of this Dicke superradiant phase transition in momentum space looks like a checkerboard. So initially you have spin down, which is just everything at rest, and then you get Bragg scattering into these 4 peaks. And that we have done, so people have done that 12 years ago just with a single mode cavity and a single BEC. Now we've done this in a multi-mode cavity with a BEC BEC at this position R2 and a BEC at this position R1. And you get a mirror image of R1 over here and a mirror image of R2 over here. That's because of the fact that you have only even modes or only odd modes. So everything you'll see in my talk will be double because of that, but never mind, it's just a detail. And what you can see is that the states of the light coming out through this holography tells us that these atoms here, when they have undergo this transition, are say spin down, which we'll call orange, and these are spin up, which we'll call blue, or 0 and pi. And so you see that they can have spatially undergo different organization of their pseudo spins because of the multimode nature of the cavity. And this is data, and this is coming from the holography. You can actually read out the phase. Or you can actually really encode spins into the system, use the pseudo spins of the hyperfine structure of the rubidium atom. And if you do that, then this diagram looks the same, except now we can color the 0 momentum spot as blue as spin down, and the higher momentum Bragg spots as spin up or red. And then when we do, when we image the atoms directly, okay, and color them based on spin, do spin detection, that we see that we can actually see organization into this collective state that is spinful. So we have spin down here, and then these Bragg peaks are spin up, and they have this interesting peanut or coffee bean looking structure. And that's because the mode that we were doing this in, just for fun, was the TM 1-0 mode, which had a node in the middle. So the phase of the photon part of the polariton flips sign in the cavity, which means that the atom part has to flip sign. And if that does that, then you get a structure factor in your Bragg peak. You get a nodal line in your Bragg peak, and we see that experimentally. So all of this shakes out that you can do motion, you can do spin, you can do any of these and call it a pseudo spin state and use this as a spin configuration computational basis. Okay, so let's, so Jonathan's going to talk a lot about this spin model and how to derive it. I'm just going to state it. It involves a polaron transformation, the unitary transformation. You take the Hamiltonian I showed you before, you apply this unitary, and after a lot of math, you can get out an equation that looks just like a spin system. So you have the modes, the Bath modes of the system, then you have the coupling of the system, has some atomic physics scaling parameters, and then there's the JIJ, and then you have the SI-SJ coupling here. This just is an Ising Hamiltonian. And the name of the game will be to make this interesting. So this connectivity Jij is going to be a sum over all these mode patterns for an atom at Ri and Rj, and there's a phase factor depending on the mode that you're summing over. We know how to analytically take these sums in relevant limits, and I'll present the answer to that in a moment. Meanwhile, this is a very interesting term here. This is the system bath coupling, which allows one to dissipate energy to the cavity modes. And what we found, and this is a paper that, well, I'm editing the final draft right now, and hopefully it will be on the archive in a week or so. It's a long paper that theoretically shows how we can use this to actually naturally dissipate out wrong spin configurations and drive the system to the right spin configurations so that it functions as a natural solver for network problems. Okay, so let's talk about this cavity-mediated interaction. So if you calculate what this looks like, then it looks like a delta function for a local interaction plus its mirror image. And this is just because it's that confocal cavity, good parity kind of thing. But you basically get a delta function plus this very bizarre non-local term. So this local term here in a cavity that's not perfectly degenerate broadens out into this Bessel function that's still short ranged. And we can experimentally measure it by taking two BCs effectively and changing their relative position to one another. And as you change the relative position to one another, you measure the interaction energy by measuring the threshold for superradiance. And as they come together, you have more interaction energy, so the threshold for interaction for the transition goes down, implying that the interaction energy goes up. And so this light blue is for a not very multimode cavity, it's kind of broad. But for a much more multimode cavity, the interaction is stronger and it's narrower. And that's basically the fact that we can control the interaction range through C. So this is given by how degenerate the cavity is. So that we've well characterized. This non-local term is something that we've discovered that it's not in any sort of literature that I've ever seen, where you have this extremely nonlinear function of this dot product of the spin at position I and a spin at position J. It's just a weird thing. But it's easily manifest in the amplitude and the phase of the light coming out. And again, we can do holography of the light coming out. And you can see that, the local part of the interaction are these bright spots here, the bright spots, but then you get this stripy pattern underneath it, which is this non-local interaction, okay? That's kind of overlaid on all of this. And so we experimentally characterizing this exactly this kind of interaction. I don't have time to tell you exactly where it comes from, but it comes from GUI phases, the summations over GUI phases, or in other words, the fact that a confocal cavity images the Fourier transform of the light back onto the scattering particles within inside the cavity. So it's a very neat optical effect that gives you some very interesting many-body physics. Okay, so to demonstrate the local interaction, again, we take a BC and we move it back and forth. In fact, we don't have to take another BC. We can just interact it with its mirror image, which is kind of a cute trick. And we can do this with a single mode cavity where we separate the modes out and we just put the pump very far away. So we're talking to a pure TM00 mode. And as you move the atoms transversely in the cavity, you can see that the amplitude of the light coming out changes because you're just looking at the envelope of the Gaussian TM00 mode. But you don't see any real change in the structure because there is no structure. It's just a single mode cavity. But now if you do this with a multi-mode cavity, not even a very good one, this one is not as good as we've made, but you see that the modes are starting to overlap. Now when you take the BC and you move it transversely and you see its mirror image, you see that they can merge together into a bright spot and separate. So you can actually see the distinct pattern because basically it's almost like you have a free space lens. You have half the modes that you have in free space up to the numerical aperture. This is why we call it an active quantum gas microscope. And basically the spot's width here is not limited by the resolution of this mirror. It's actually just limited by the size of the BC where we're able to trap in our tweezer and crunch down. It's a few microns. In principle, we can go much smaller. So in fact, what we're measuring right now, and we've already put a bound on, is that this small mode waste is actually proportional to how many modes are participating in the coupling. And even so, we have a cooperativity for those of you who know cavity QED. Your strong coupling is limit is, given by a cooperativity greater than 1. For a single atom coupled to just a single mode TM00 cavity, the cooperativity is about 2 or 3. But now you have mode after mode after mode after mode superimposed on this in a coherent fashion. You boost up that single particle cooperativity up to more than 100. We're trying to make this measure this exactly right now, but it's one of the highest cooperativity systems that have ever been created in the world. And that's really exciting for making high fidelity quantum states. All right, so let me focus again on this connectivity, but now I'll go back to this, this term that arises due to the GUI phases, this non-local term. So this is the kind of textbook paraxial optics picture of a confocal cavity. You get this hourglass mode, but if you actually calculate what the field looks like, it's far more complicated. And all of these little ripples here are actually due to this term over here, okay? And so if you put atoms in there and then take a hologram of the light coming out, you can directly read out this zero phase or blue or pi phase or orange. You can directly read that out onto a camera, and this is what that looks like for 5 atoms, and these are the mirror images over here. You get some very complicated pattern, but you can see, you can look at the local interaction to tell you the spin state of the atoms. Some are blue, which are, let's call them spin up, and some are orange, let's call those spin down, okay? And then moreover, this is a long range term, it's non-local. It provides all-to-all connectivity with sign changing. And it's the sign changing aspect of it that is just really fascinating and gives us the complexity necessary to do interesting computational dynamics and physics. So the local interaction provides spin state detection and efficient dissipation channels. And then the long range non-local term provides the connectivity. All right, so let's characterize this interaction in a confocal cavity. I alluded to the fact that we can take holograms. I can put a more of a underline over that. We beat the local oscillator onto the camera here. This is some raw images. We can pull out the amplitude and the phase and reconstruct it like so. So I'll just skip over this quickly. All right, so now we've characterized the local interaction experimentally. Let's characterize the non-local interaction experimentally. Again, this is some of that data before, but now I'm going to tell you a little bit more about it. We take 2 actual clumps of atoms, and then of course you get the mirror image, and you move them with respect to another. Let's put one in the center of the cavity so it's overlapping with this mirror image, and then one far away so you only see 3 dots. Here, it turns out that the phase of this dot product here means that the JIJs are all positive, which means that they're ferromagnetically interacting. Let's call that blue. And then as you move this central clump of atoms away, then at some point you start to hit a node of this, an antinode of the cosine, and then you start to flip the sign of the spins until all the spins are anti-ferromagnetically coupled. So this is ferromagnet and this is anti-ferromagnet. Now this is just for 2 spins. What we'd like to do, what we're starting to do now, is to move this to 3 to 10 and eventually to hundreds and so forth of spins. So what can you do with this? And this is the work, the theory work, and this is basically an abstract for Jonathan's talk that will begin in a few minutes. But just to give you a taste of what we have done theoretically to show the power of this system, let me give you some hand-wavy results. So the dissipation in the system we have determined realizes physically steepest descent dynamics. So if you say take 3 spins, and these are collective spin operators, so they're either plus n spins or minus n spins in that particular clump, and then you flip these 3 in the wrong way compared to an optimal configuration with respect to the rest of them, as a function of time, they will flip in order to correct that errant spin configuration, and they will flip in such a way that the greatest energy dissipated, the one that when you flip the spin brings you furthest down in the energy landscape, happens first. So this is steepest descent dynamics, and you get this staircase-like behavior. And this works very efficiently and in this fashion because you have this nice engineered bath due to the cavity separating out or making special certain modes over others. And so if you read detune, then this tail over here is given in such a way that your rate constants for flipping are accentuated for ones that dissipate energy and suppressed for ones that gain energy. And that's just a way in which you can use physical dynamics to give you steepest descent. And this is really nice because the steepest descent in a fashion that you don't have to calculate where the gradient is, which is a computational bottleneck on a Van Neumann machine, you know, like my desktop right here. The physical system itself just knows which is the steepest descent direction to go in, and it goes into it. So for equal rate flips of a computer versus this physical system, the physical system will be more efficient. Okay, so we can use this in an associative memory. So what's an associative memory? You know, the Hopfield network is a model for this, where you, in the structure of the JIJ matrix, you embed patterns. So you can have a really great pattern like this S, and one that is not very good pattern that reads cal. And then if you corrupt these inputs by distorting them and then feed that into the dynamical system, for us that could be shining it into the mirror directly, seeding the cavity directly, the Hamiltonian dynamics of the system will correct the outputs to give you your really nice image and your not so nice image right here. Okay, I'm a little biased, I guess. What the system does not do is Glauber dynamics. Glauber dynamics are simple to implement in terms of a stochastic walk down the energy landscape, but they're not very efficient. It does something much better, which is a greedy descent or steepest descent dynamics. It naturally computes, quote unquote, the energy cost of flipping every spin, and then flips the one that lowers the energy most. And that's really a neat thing, very powerful thing. So we can test this by kind of looking at some test system where you have some stored memories and some energy landscape. This is the classic picture for a Hopfield associative memory. So you have, say, you know, one memory here. This is, say, Stanford. This is Cal. This is Pitt over here. And then you flip some spins, and then you see, you know, how many spins and some Hamming distance can you flip before you no longer go back dynamically to the right state, but you cross over into some other valley. And what we can see is that we can just do this, and we can see that you get the, you know, if you start with the right input, the dynamics, you don't see any spin flips. That's these black lines. They just go to the right spot that they started with. But if you flip some spins at some Hamming distance away, then they reorder in such a way to give you the right dynamics. And so the upshot of this is that the cavity dynamics, so if you look at the recall probability, the probability of coming back to the right state, given some errors at some Hamming distance away, if you do this with zero temperature metropolis, Hastings metropolis dynamics in this red line, your recall probability drops off very rapidly, only maybe 5 Hamming distances away or 4 Hamming distances away. But kind of miraculously, when you have steepest descent dynamics, it effectively enlarges the basins of attraction, meaning that you can store more memories and store each memory with higher fidelity. So not only can steepest descent be more efficient in the physical system, but it also gives you more memories and larger basins, so larger fidelities. And that's just an amazing thing that we discovered. Okay, and last, you know, from a scientific standpoint, you know, the system undergoes a ferromagnetic to spin glass transition. And that transition happens as a function of the width of these spins, the clumps of spins within the cavity, given by this parameter W naught. And as you spread them out more and more, this cosine R dot R prime wraps its phase more and more rapidly, and you start to get a distribution of the GIJs that's more equally bimodal between -1 and +1, and this becomes a spin glass, which we know is true because we can do the statistics of this distribution, and it looks like a Wigner semicircle or Wigner-Dyson statistics. So that's really exciting because in this intermediate regime, you can make the associative memories that I just talked about. But in this regime, you can address optimization problems encoded in the GIJ and explore in this quantum optical system. And that's what we'll be exploring in the future. Okay, so let me conclude now. So Jonathan Keeling here will describe some of the theory, the next talk. Multimode cavity QED naturally realizes a neural network, and we've shown, and the paper will be coming out soon, that it implements efficient dynamics for dissipating energy in wrong spin configurations. Experimentally, we've demonstrated all the necessary ingredients for at least associative memory, and we can go beyond that to combinatorial optimization in the future. So the outlook is to study more and more quantum effects at the quantum critical phase transition. This is a hard thing to do numerically. Andrew Daly and his team are helping us to look at this using some special techniques that they and Jonathan Keeling have developed. And then experimentally, we can get deeper into the quantum regime by using fewer atoms per node to reduce the length of the collective spin vector. And we can do that by enhancing the coupling of each atom to the cavity. All right, so with that, again, I'll put up the entire team. Again, these are the theory collaborators. These are specific grad students on this project, gracious funding from NTT and especially ARO. And then, of course, we have other experiments that do other fun things that I can tell you about at some other day. Thank you very much.
Thanks so much, Ben. Let's give Ben a round of applause. If anyone has questions, you may just raise your hand on Zoom. There's a feature, or send me a chat message to indicate. So I will just unmute you as we have done in the last couple of days. I also want to take this a moment to say we have 3 speakers. This is more like a drive-in dissipation session today. Very exciting. This is one of the frontiers. Let me see if anyone has questions already. How many hands on? Natanya, let me unmute you. Laura is very active.
Oh yes, hi. Thanks, Ben. Exciting talk. Really enjoyed it. Great work. I have a question about JIJ. So you mentioned how flexible JIJs are, but what are the limitations?
Okay, so may I answer that in 2 ways? So first, I just presented one form of the JIJs. So with this kind of cosine R1.R2, we actually know of ways to engineer our laser pumping schemes to, for instance, make an RKKY interaction or a multi-component Mattis model. So there's a lot of things that we can do.
Local, you can do local Hamiltonians then as well.
Yes, yes. So we have things that are just local, like RKKY, things that are very non-local, like Mattis model, somewhere in the middle, which is what we showed. So we can do a lot of those things. Now, the complication is that, you know, while we know if we put in locations of spins, what JIJ we get out, the inverse problem is in itself a very difficult problem. Yeah. So if you tell me I want to solve this particular graph, it actually takes some work to figure out where to put the atoms, at least for the cosine term. Now this cosine R1 type form, if we did RKKY, then it would be an easy invertible problem. But the one that we showed you is a little bit more difficult, but that's okay.
But that's why you're thinking about associative memory, because you don't need to actually control, you know, independently JIJs. It's enough for you to have spin glass, right? It's enough for you to have a variety of couplings, complex coupling.
Yeah, and then post facto, and then you can just figure out where all the minimums are, and then we have a scheme, a linear scheme actually, so it's efficient, that maps those naturally occurring minima to memories that we care about. So that's easy. If you want to do some like max cut problem, then that's a little bit trickier, but then you might want to use RKKY instead.
Okay, thanks. But also, can I ask the last question? What is the advantage then? Because you still, the method as you presented it, it's like simulated annealing, right? You go down the hill and then you flip the spin.
Oh, yeah.
So why would it be advantage? You know, what is the advantage in comparison if I do it on Neumann architecture?
Right. So everything I told you now is in the semi-classical regime, where we're well above a threshold, and indeed we're coming down some effective energy landscape. So yeah, it's kind of like that, but we're already starting pretty close, because when you go through that threshold, just like you know from coherent IC machines or whatever, you condense into a state that's already pretty close. Okay, how that actually works, we're not sure. Nobody is actually. And that's something that we have to think about.
Great. In view of time, maybe just with one more question from the chat. Thank you, Latanya. So maybe we're going to talk later in the panel discussion session. So there's a question from Shovik. He actually told me his microphone is not working, so he asked me to convey to Ben. I believe he's actually from Dave's group. He's a very good student, I posted, I think. So he said, could you ask Ben how dissipation leads to area correction?
Well, it's simply the notion that, okay, it's not error. I always put quotes around the error correction because it's not error correction in the digital computing sense. It's just the fact that if you have a wrong configuration that has a higher cost functional expectation, then the dissipation then removes that configuration, and the pumping in the systems replaces it with a configuration that has a lower expectation of that cost functional. Okay, so it allows you to throw away the junk and repopulate with the good stuff.
Great, thank you, Ben. Let's move on to our next speaker, Jonathan. So okay. Ben, could you?
Yes, I will stop sharing.
Stop sharing, and then Jonathan can take over.